Good evening. This is a live session for rheology of complex materials. We will wait for some of the questions from your side, and it would be very nice if you could raise some questions, and then we can have a more interactive session where whichever questions that you have based on the lectures that we have done so far or the assignments that we have done, then we can answer some of those questions, because it's very likely that the question that one person has, few others may also have the same question. So as I'm waiting for some of your responses and questions, what I thought we can start with is looking at some of the geometries. We have talked about many of these geometries in the rheology course so far, and we've only seen them through either diagrams or through sketches, and so I thought we can look at some of them and see what is the actual setup in which rheology is done. And so if you see this, this is a parallel plate. So this is what we've been drawing as a sketch, and whenever in I think I have to tell them. So we've been drawing this parallel plate, and so this is the parallel plate basically. If you look at, so this is 25 mm diameter or 1 inch, and usually the other rheometer plate will also be there at the bottom. So we place the fluid here and then put the geometry and then start rotating. So this is what the overall parallel plate geometry is. But actually, as I've been also saying, that there are various geometries, and the geometries depend on the kind of application that we might have. And I'll show you an example. The most, think of it as to so the three parallel plates that we discussed, we can continue on and look at this other geometry, which is very useful for low viscosity materials generally. And the question then is, why is this useful for low viscosity fluids? And so this is the cup in which sample would be taken, and then this bob would be lowered, and then the bob will do the rheological experiment that we would prescribe. For example, we may do an oscillatory shear, in which case the bob will basically go back and forth. So the question is, why would you use this kind of a geometry compared to parallel plate, which we saw earlier? In case of parallel plate, you can see that the overall area over which shear is being applied is this circular area here. So sample is here and then shear is being applied. While in this case, what you have is this overall cylindrical area over which shearing takes place. Now, another interesting features that you can try to again answer for is this conical shape that is given at the bottom. In class, whenever we have drawn the concentric cylinders, we've sort of drawn an idealized geometry where we said that this is the inner cylinder and this is what would rotate, and then we have the outer cylinder. So therefore we've just been drawing, because anyway shearing is happen only in this region. So this is the region of shearing. So why is it that instrument, when geometries are being designed, one would make a conical shape at the bottom of the geometry? So that's something for you to think about. And so just to give one answer for this is useful for asphalt. So the question that you can try to answer is, why would this kind of a geometry where the shearing is happening over a very small area, So compared to this parallel plate, what we have is an extremely small parallel plate, and then so shearing, what would be done is fluid will be kept here, and this is more often will be asphalt, as I said, and then there is a bottom plate. So why would it make sense to use this kind of a geometry for asphalt? It's something you can think of. And another geometry, this is transparent geometry. So whenever we need microstructure of the material, and it's possible to view the microstructure through just either a microscope, then this kind of a geometry can be used, because you can view the material from top. So these are some examples of parallel plate and concentric cylinder geometries which are used, and you can see that there is a finer aspect of devising a geometry for a particular application. So for asphalt there is a different kind of parallel plate. For materials which have microstructure, we use a different kind of parallel plates. The other thing that sort of may be very surprising is when you look at parallel plate and cone. So in class again, through our lectures, we've been trying to draw cone, and we've been sort of magnifying and so we've been saying this is the cone angle, and of course we have specified that the cone angle is usually 1 to 4 degrees. So this drawing is actually quite misleading in the sense that the cone is, the angle is so small that if we look at this through naked eye, it's very difficult to make out that it's a cone. It's very similar. This is parallel plate and this is cone. So only when you look at it very closely, then you can make out that there is a small angle, and this is the top cone which will rotate in case of rheology where fluid is placed here. So many of these things come as part of the operations of rheometer and trying to work with various different types of materials. Quite often we will have to make a choice of which geometry to use for which material, and answer would usually, there is no sort of golden standard or a handbook where you can go and look and say for this particular material, for this kind of application, use this geometry. Many of these things come from trial and error. There are some general guidelines. One question that you could try to think of is the following: that we have two parallel plates here in our lab, for example, and generally also rheometers will come with parallel plates of different diameter. So one is this diameter, this one is. So why would you, in fact this is a cone, this is cone. So let me just put the parallel plate back. See, only when I saw it very closely, then I could make out that it's a cone. So that's the point I was trying to make earlier, that by just looking at it from far, it's very difficult. So now both of these are cones. So now why would I use this cone or why would I use this cone? And what would be the advantage or disadvantage of using a very large cone? What would be the advantage or disadvantage of using a very small cone? So that's something for, and some of these things we have been discussing in class. It may be a sort of whatever we have learned, we have to try to use those concepts to try to justify what may be the differences between these two geometries. So we will, are there any questions? No questions, okay. So we will just continue on. In fact, this is a very interesting geometry, which is where we can test materials which are extremely low viscosity. So it's called double gap. So anytime, in this case, if you see the cup itself, the bob itself is also hollow, while the earlier bob that I showed is actually solid. So in this case, the inner region is also in fact annular. So let me just draw a quick sketch of this. So instead of having a fluid between two cylinders like this, what we have is a slightly different arrangement. So the bottom piece looks something like this, and this is connected. So the fluid will be kept here and here also. So here also and here also. So this bob which is rotating will see fluid on both sides, and the stationary surfaces are these. This is one stationary surface and this is the other stationary surface. So that's why this is called a double gap. So again, when viscosities are extremely low, such geometries are very useful. Now look at this geometry. Very unlike anything that we have discussed in class so far. In fact, in class our whole emphasis has been on rheometric flows which are controlled, and quite often you would have heard me emphasizing one-dimensional flow and so on. And if I take material in this kind of a geometry and then put this geometry and rotate, clearly the flow is going to be very complicated. Why would I use this kind of a geometry? For what materials it may be useful to not have parallel plate or cone and plate or concentric cylinder, but this kind of a geometry. So that's something for you to think about. So what we have done for the next part of the lecture, this session, is to move on, and given that all these plethora of geometries are available, and we usually work with several different materials, if we use any one of them and then collect some data, how do we sort of assess? What's the reliability of data? Is it repeatable? Is there some portion of the data I should be more careful in redoing? Are there hints to suggest that some data looks, maybe instrument is either being stretched to its sensitivity limits, either at the lower end or upper end? So those are very important from the point of view of a person who is measuring rheological properties. And quite often in R&D, of course, we are trying to work with new materials. So we may not have guidelines, we may not know what the response of the material is already. In fact, that's why we are trying to do R&D on it. In case of a standard industrial sample also, if we are doing a check in terms of quality testing, we would like to know whether it's the instrument performance or if it's the material problem. If, let's say, we see a sample which shows a response which is unexpected. So many of these cases we would like to examine the data a little more closely. So in the remaining time in the session, what I'll try to do is to show some of these data, and then we can try to ask questions and see if we can try to see the finer points of rheological data, and then try to assess whether these data are reasonable, they are not reasonable, how should I do my next experiment, and so on. So one useful thing which is there in any instrument is to have some standards. So whenever we are trying to measure something, in case of rheology, silicon oils are used as standards. So these are available from various vendors, and these are fluids of standard viscosity. So we know what the response of this material is, and to check the working of our instrument, to check the conditions under which we are measuring, it's useful to always use these standard fluids. So first off, I'll show some data Again, as I said, this is done by Ramya. So this is to examine what kind of data are we getting, and whether we know the limitations of the instrument. So if you look at the right hand side graph first, what we have is viscosity as a function of shear rate, and silicon oils are all Newtonian fluids, so we would expect viscosity to be constant. And what is shown here is, yes, viscosity is indeed constant, but if you look at low strain rates, there seems to be viscosity is very fluctuating. There seems to be some noise in the data. One conclusion that you may feel like drawing is the fact that this is a shear thinning sample. For example, the viscosity is around 10 at 10 to the power minus 2, and then it decreases to 1 Pascal second by the time the shear rate is 10 to the power minus 1. So the question is this kind of conclusion warranted? Should we say that this is Newtonian, so something here is noisy, or no, the material is shear thinning up to 10 to the power minus 1, and after that it becomes constant viscosity? So in this case, of course, as I said, it's a standard fluid, so we know the answer, and that's why therefore these are very useful to look at the limitations of the rheometer operation. So in this case, we can clearly see that this is supposed to be, the green stars are supposed to be 1000 centipoise, and if you remember, the conversion between 1 Pascal second is 10 to the power minus 3 Pascal second is 1 centipoise, or so 1000 centipoise will be 1 Pascal second. So this viscosity of the fluid should be 1 Pascal second, which is what you see, and clearly below this strain rate there is some limitations of the instrument. Now the question is, what might be that limitation? So one way to think of the limitation is to say that what would be the stress that is experienced or that is applied by the rheometer on the sample, and stress will be directly related to the torque that is being applied by the rheometer. As we have always said in the class during the lectures, that we have rotation, and the rotation is achieved by applying a torque on the sample, and of course this rotating torque leads to shear stress on the material. And of course we know at the material level, shear stress and shear rate, shear strain rate or shear strain, they are all related, but at the instrument level what we are trying to do is measurement of torque or application of torque, and similarly measurement of rotation or application of rotation. So we could also just do a rotation which is rotated for some degree, then we are applying a rotational strain, or we could keep rotating it, then we are applying a steady rotation, or we could oscillate it in some 2 degree, so then we are doing steady, we are doing oscillation. So therefore in this case also one could think of possibilities in terms of, is there a problem in maybe instrument is not able to apply this 10 to the power minus 2 strain rate. In the sense the control on the instrument, when we are trying to tell it to rotate very slowly, it does this. Since it can't really rotate very slowly, therefore it's doing it in jerks. And a consequence of such motion, because it was clear when we said we are doing rheology, the strain rate should be constant, which means the rotation should change at a constant rate. And clearly if that's not happening, if there are jerks because the instrument is not able to control, then there is a possibility that the viscosity value that we get will be all over the place, because now the flow is no longer what we assumed it to be, and so clearly the torque will also be then be different. So that's one possibility. Given that there is a left hand side graph, what you could also see is that what happens to the torque values, and as we know, for a Newtonian fluid, stress is proportional to strain rate multiplied by viscosity. So what we have is the overall torque which is related to stress, so stress is viscosity times strain rate, and this stress is directly related to torque. So if I test a fluid at higher strain rate, stress will be higher, torque will be higher. Or if I test a fluid of higher viscosity, stress will be larger and torque will be larger. So, but what if I test a fluid of very low viscosity and at very low strain rate? So if I measure the viscosity is also low, strain rate is also low, then the stress will be very low and torque will be very low, and which is what can be seen in the left hand side graph. For example, the 4 centipoise fluid, which is in red here, you can see that this is the general range which is specified by the instrument company itself. So you can see that when you are operating, the data is much lower than in fact what is suggested also. And many times, many of the instruments, whenever you are near the limit, even if slightly higher than the limit, you will always have to be careful regarding the overall response that you are getting and how reliable is this. So for example, what I was pointing out, that this data also seems little suspect. In fact, if you look at it from the torque point of view, it has a slightly higher torque than what is the lowest specified limit. So one therefore will have to look at even the strain rate, strain as a function of time, to see if it's a constant strain rate or not. And one would also have to look at what might be the other features of rheometer control that might give us this kind of data. So if, let's say, I am interested in an unknown fluid and I get some result like this green, it is better for me to assume that looks like it's a Newtonian fluid. There is some evidence to suggest that maybe there are some features, but we are so close to the instrument operating limits that it's not a good idea for us to make conclusions based on this data. The other thing, of course, one can do is repeat this experiment. So if you do this 2-3 times, and what you will see is in this range there will be lot of scatter of data. So again, that indicates that this is basically related to instrument operation limitations. So are there any questions? No? Okay. So what we will look at is also the same samples. Now if you measure the information at different, as a function of time, but at very low strain rate. So if you just look at here, this is the 0.1 strain rate. So this is also something that can be done if you want to see whether this data is reliable or not. What you can do is you can measure at the constant strain rate but collect multiple data points. So in the next slide we have taken the same same 3 fluids, and now at very low strain rates, where we expected the red and blue to be suspect because we are definitely in the torque limit, which is lower than what the instrument limit is, and the green data is seems to be okay because it's above the limit. And so if you look at the data now, you can see that as time goes by, each and every data point that we get for the green, which is the 1000 centipoise fluid, we basically have no variation. So the measurement is being done quite accurately. One other thing that you can notice is the fact that if I just wait in between, if I just stop shearing, so I give some waiting time and then again start the experiment, and so in this TW period the rheometer was stopped, and you can see immediately when you start the experiment again you get exactly the same results. So these are some ways of checks and balances to what can be called a sanity check. In case you are seeing results which are very odd for a new material, or the results that you are doing is the same material that is reported in literature, or you are in industry where you are trying to do a quality check, if though suddenly there is a mismatch, these kind of tests will ensure that the geometry is okay, the rheometer is okay, the conditions under which the tests are being done are okay. So clearly material, there is something gone different, and then so therefore you can do troubleshooting with respect to the material itself. Yeah. Again the same question. Okay. So generally rheology is rheology's scope is to understand the materials deformation behavior. And if you look at the introductory blurb of this course, we have various materials such as shampoos and toothpastes and jams and jellies which we use in our day-to-day life, and each of them has a very well defined deformation behavior. Similarly, we have several other materials such as paints which we use for painting at homes. Paints are also used as coatings in variety of applications in automotive or any other application. So again, paint would require to have a specific deformation behavior. We can study liquids also, we can study solid like materials also using rheology, and we can also study the solid to liquid transition. And in fact in the lectures which are going to be maybe 2-3 lectures down the line, we will look at some of the experimental data where we will look at solid like materials, we will also look at liquid like materials, and we will also look at some materials which undergo this transition from liquid like to solid like. So rheology can be useful for any of these three kind of materials, whether they stay liquid like, whether they stay solid like, or whether they are undergoing transition. We will also see some data which is from textbooks or from some research papers, and that will give you an idea as to how rheology is useful to look at liquid like materials or solid like materials or materials which are undergoing transition. Okay, so silicon oil, see, so a lot of these things would depend on how reliable and stable the material is. If you look at silicon oil as a material, silicon oils are used as heat transfer fluids because they are very stable materials. And when you want to use a standard material, you would want it to remain very stable over, and it should have a reasonable shelf life. And so silicon oils therefore have evolved as standard fluids which are used as viscosity standards. In fact, but as I have said, these are Newtonian fluid standards, and clearly in this course we have seen that our main interest is in viscoelastic materials. So for viscoelastic materials there are different standards, and so in fact one of the materials that could be useful as a standard is what is the data shown here. And these class of materials are also, if you look at various demonstrations and all that, there will be silly putty or some jelly like things which are useful to describe the viscoelasticity and how materials can have a very complex behavior. So polyvinyl alcohol and boric acid. So this data again is showing one such material. So here you can see that we are looking at oscillatory shear data, and this is a viscoelastic sample. At low frequencies you have G prime much lower than G double prime, and then they become equal at some frequency, and then G prime starts becoming constant while G double prime undergoes a minimum and it increases. During class we have already discussed this kind of a material, viscoelastic material. We had seen that supramolecular gel also has a similar response. So, some of the instrument companies give standard materials which are viscoelastic standards like these, because the silicon oil that we were discussing earlier can only give you Newtonian response. So, if you want to look at how accurately the viscoelastic characteristics are being measured, you may have to look at a viscoelastic standard. But one thing which you should remember is in the end the ability of instrument to do viscoelastic measurement in the end depends on how accurately it's capturing torque and how accurately it's capturing rotation. And this test on Newtonian fluids does both of that. It tests for torque, it tests for rotation. So therefore, we continue to use silicon oils as standard oils most of the time. So now, if you look at this PVA borax sample here data, what the intention of showing this is to see how good the repeatability is and where the repeatability will be little less and how reliable this data is. So if you look at the 3 repeats, so they are in black, red and blue colors, and you can see that the overall repeatability is quite good, except maybe at very low frequencies where G prime seems to be slightly different compared to each other. One of the general guidelines that sometimes you will have to think of is in terms of, therefore if I measure a G prime at let's say 10 to the power minus 1 radian per second for this particular material, should I call it 0.1, 0.2, 0.3, 0.4? So shall I call it 0.3 or 0.4? So there seems to be that much variation in terms of different repeats. So is it okay for me if I have 2 such materials, if one of them I get 0.3, another one I get 0.5, should I conclude that, oh, the difference between them is significant and material has, one has a higher G prime than the other? Looking at this kind of repeats, the answer would be no. So unless there is a significant difference between 2 different materials, we should not really look at such small differences. So therefore repeatability of course always is desirable in any experimental program that we do. Other important thing from a rheometer point of view is you can again see that low frequencies where the issue may be, and again because when you have very low frequencies you again have less torques, and therefore again instrument sensitivity is a problem. In class we have also discussed that at high frequencies sometimes you may encounter problems, and this would be the other effects, which is we have termed it as inertial effects. Given that we are in oscillatory test, we are doing this to the geometry where it's going back and forth, the fluid is also expected to go back and forth, and but if there is fluid inertia, then fluid will go a little bit more and then only turn around, and so there will be an inertial effect of the fluid. You remember that inertia means the tendency of the material to move if it is moving, or if it is stopped then it remains stopped. So therefore inertial effects can in fact play a significant role at higher frequency. So one question that can be raised for let's say this kind of a data is the following, that yes, there is good repeatability at high frequency, but for all the 3 samples there is inertial effects dominant. So in that case what you can say is the data is repeatable, but it's not accurate, it's not reliable because inertial effects are there. So to check for inertial effects, then you will have to do different things. First of all, you will have to see what's the nominal viscosity of this fluid. You will have to estimate the Reynolds numbers, and then you will have to then try to justify whether inertial effects are insignificant or significant. The right hand side graph is again a repeat, but this time when strain amplitude is varied. During course we have already seen, if we are let's say using cone and plate geometry, we use strain. So this is the strain amplitude. and generally this is mentioned as a percent, and so what we have here is the storage modulus G prime or loss modulus G double prime as a function of strain amplitude. And so the question is, can you spot the limit of nonlinear response or the limit of linear response using such data? So that's something for you to think about. So because we have discussed in class linear viscoelasticity, and we have also discussed what happens if the material response is not in the linear regime. So if this kind of data is obtained, can this indicate to us where is the linear limit? At what strain percentage, up to what strain percentage the material response can be termed as linear, and up to what, beyond what strain percentage the material response is non-linear. So I will leave you to think about this, and if there are any doubts you can again post them on the forum later on also. In the beginning of the lecture we sort of looked at all these different geometries, cone and plate, parallel plate, cup and bob, and so quite often again while doing rheology one has this question of which geometry to use for which kind of sample. There are some guidelines of course, and when you are working on a material which others have looked at, you can always say that I will follow whatever has been done by others and then continue to use it. But in general sometimes it is useful to ask the question as to which geometry is appropriate for which material. And so here there is just two geometries which we have discussed in class quite a lot, cone and plate and parallel plate. And if you look at the bottom of the slide, it's written uniform flow field and non-homogeneous flow field. What I would like you to think of is why is this? What is meant by uniform flow field and what is meant by non-homogeneous flow field? And I think maybe in one of the lectures we have discussed this, but how would you say that in which way the flow in cone and plate ends up being uniform, in which respect is it uniform, and why is it non-homogeneous or non-uniform in case of parallel plate? So, but from an application point of view or from an analysis point of view, if I use the same material in these two different geometries, how good is the comparison between different materials? So, the slide here just shows different materials being tested in two different geometries. On the left side we have cone and plate, and on the right side we have parallel plate. So if you just look at the data, we have right at this point of time we don't need to sort of focus on what those things mean, but you can see that on the left hand side the solid line is HA, while the right hand side also solid line is HA. And so what would be your observations when you sort of look at these two sets of data? 5 different samples done on 2 different geometries, where viscosity is being plotted as a function of strain rate or shear rate. So if you look at the two data, what kind of observations can be made? If I do the usual eye test, which is kind of done, say that cover one part and then cover the other part and which one is different, the immediate instinct may be to say that okay, both of them look very similar. If I flash one or the other immediately and not let you look at it for a long time, then you might say okay, broadly it's the same response. So that's the first sort of observation, that it looks similar, and this is something which we also ought to expect, because in the end, using rheology, our idea is to characterize material response, and material response should not depend on what is the nature of the geometry being used, what is the overall details regarding the rheometric measurements, because in the end we would like to look at viscosity as the property, and we would like to use the numbers that are generated in these tests for doing some further calculations or further estimations. So therefore, we are interested in only the viscosity itself, which is a material behavior. And so here broadly, if you see the solid line itself on the top, we can see that it starts off at similar values and it goes on, but you can see that there are some finer differences. At low strain rates, parallel plate seems to have some fluctuations. Okay, so then what you can then try to do is to examine the torque for such measurements and then see whether there are any limitations. If you can spot any other differences, again you can write to us later on, and then we can try to sort of examine them in little more carefully. Right now, at least immediately highlighting, I can't see any other difference. I can see also, for example, the circles and the stars are much more different, but everything is related to these low strain rates. From 0.1 to 1, basically the low viscosity materials in parallel plate seem to have some fluctuations in data. Now again you will not find any information in any of the resource to say that is this a real material response or this is an artifact or this is something where whatever are the assumptions I made during rheological analysis, those assumptions are not valid. So what one has to do is to do more systematic experiments. You can maybe measure at let's say strain rate of 0.3 as a function of time to see how reliable and repeatable these results are. That's one way of doing it. You can also sometimes do some systematic analysis of composition itself. So in this range, if you change the composition and if you get a systematic result, then you can explain it based on the mechanisms which are related to composition, then again you can say the reliability is better. So therefore, most of these kind of measurements when we are trying to do for new materials, we really don't have any guidelines which are present from earlier. Now we can again look at another set of measurements. This is also a case of oscillatory shear, and in this case again you can see that at very high, low and high frequency the data seems to be different compared to generally it won't drop. Serious. So what we have done using the green circles is again to highlight the fact that at very high frequency and at very low frequency there seems to be a difference. And again in parallel plate case, the data seem to be showing some fluctuations. And again, so these are the data when you examine, then one needs to look at much more carefully and try to see whether we can justify these data being real, or we conclude that these data are actually part of the instrument limitations or noise that is being there. We have discussed the relaxation time as a key characteristic of the material, and if you recall, when omega lambda is 1, that's where G prime is equal to G double prime. So therefore this point at which G prime and G double prime cross over, that frequency indicating crossover frequency is the inverse of relaxation time. So if we were measuring the relaxation time using these two different geometries, the black one is cone and plate and the red one is parallel plate. So you can see that the relaxation time is different. In one case, the crossover frequency happens to be, you can see here that it's 2, 3, 4, 5, between 5 and 6, and the other one is between 7 and 8. So So therefore, one case we are getting somewhere around here, the other case maybe we are getting here. So therefore, the frequency at which the crossover happens is slightly different, and therefore the relaxation time that is calculated will be 1.55 or 1.75. So now the question is, which of this is more reliable value? Can I a priori judge that? Should I rely more on the conical plate? Should I rely more on the parallel plate? And then to think of those, again it's better idea to think of what is the characteristic flow, what is the rheometric flow in case of a conical plate and in case of a parallel plate. And then one can try to answer as to if we as rheologists or we somebody who has done this measurement, if we have to say which one I would trust more, whether it will be the conical plate value or whether it will be the parallel plate value. So that's something you can think of. In fact, the answer may also be there based on just examining these data here itself to see if there seems to be more reliability in one set of data than the other. So with these we have reviewed the overall geometry, set of geometries, and how some experimental data, when it's collected, how it's can be examined. We have always seen that instrument limits is one critical issue all the time that one has to look at. Limits of linearity, limits of non-linearity is also something which we always should examine. And so with this session, then we have summarized some key guidelines which can be useful to while doing experimental characterization of the complex materials. No questions. I think we can stop. Huh? Yeah, you can post them on the forum. Yeah, an assignment is yeah. So if there are any questions, you can still post them on the forum after watching this session once more, and then we can continue the discussion on the forum. Yeah. Well, we'll still be here for another 4 to 5 minutes. So if there are still any questions, you can still post them.